All right, so we're going to do 4-4 systems as models. So basically what we're doing here is word problems. When you use systems of equations to solve word problems in the real world. So using function notation, f of x terminology with real world mathematical models. Okay, so this problem, we're going to go through this problem. This is on page 64 of your packet, actually 64 and 65. It's 2 pages. And then we're going to go through a second problem that's on page 66. All right, so this is a hot pursuit problem. There's a Coast Guard cutter, cutter's just a kind of boat, is in pursuit of a suspected drug smuggler's boat in the Gulf of Mexico. Okay. Now, the nice thing about this problem, sometimes what they'll do is they'll actually define your variables for you. That helps. Then you don't have to define them. You don't have to worry about defining them differently than I might define them. But when they define them for you, make sure you read that carefully and make sure you follow how they define them. Sometimes students will read this and then later on they define the variables differently, which can get confusing. Okay. So X is the number of minutes since the pursuit began. So at some point, this drug smuggler is, driving their boat across the water, and the Coast Guard at some point starts chasing them. So X is the number of minutes since the pursuit began. We don't quite know when it began. Okay, but C of X is the number of miles the cutter is from the station, the radar station, and S of X is the number of miles the smuggler is from the radar station. Okay. So I'm guessing somebody at some point called the radar station and said, "There he is," or "There they are," and then then the pursuit began. Okay, so you have a number of minutes, and you have a number of miles. So you have a distance and a time. And if you can remember this, sometimes this is helpful. You might remember this: distance equals rate times time. Okay, which makes sense if you're thinking of something in miles per hour. A rate is like a miles per hour. Time would be maybe in hours, and distance would maybe be in miles, and the units will work out. So miles per hour times hour, the hours cancel, and you get a distance on the left side. This multiplied together gives you a distance. Okay. So suppose the following function values are known. C of 10 equals 6.5. C of 20 equals 11.6. Okay, think of what that means. The number in parentheses, your x value. So this is when x is 10. Your y value or your output is 6.5. So right away, I'm going to write an ordered pair. 10, comma, 6.5. Your input, your x value is 20. Your output's 11.6. Okay, so that's on your C function, your C of X function. Remember what the C of X function is. It's the number of miles the cutter is from the radar station. The cutter is just one of the boats, the boat that the Coast Guard is in. And then this one, this is where the smuggler is. So at 10 minutes after the pursuit began, the smuggler is 12.1 miles from the radar station. And your input is 20 minutes after the pursuit, 15.5 miles from the radar station. Okay. How do you pronounce or define the words C of X and S of X? Okay, so that's how you say this. Some people want to say CX. It's like you say F of X. The way you say this is F of X. Okay, so the way you pronounce this is C of X. The way you pronounce this is S of X. Okay. How do you define in words? Well, these are actually defined up here. C of X is the number of miles the cutter is from the radar station. S of X is the number of miles the smuggler is from the radar station. Or more generically, C of X is your output when X is your input. S of X is your output when your X is your input. Okay. Write the real world meaning of C of 10 equals 6.5. Well, that means 10 minutes. All we have to do is look at how it's defined. 10 minutes after the pursuit began, the cutter, Coast Guard cutter, is 6.5 C of x is defined as the number of miles from this radar station. Is 6.5 miles from the radar station. Okay. Suppose that the function c and the function s are both linear functions. Find the particular equations for c of x and s of x. Well, for c of x, the cutter, I'm going to put this over here, and then the s of x, or I'll say the smuggler, the s of x, okay? So this one, we've got two ordered pairs on the cutter. We've got these two ordered pairs right here. So 10, 6.5, and 20, 11.6. We have to come up with that equation. We know it's linear, so we can put this in the form of slope-intercept form, y equals mx plus b. So your slope is equal to y2 minus y1 over x2 minus x1. Your slope comes out to 0.51. Okay, so your c of x equals your slope 0.51x plus b. Okay, I'm going to have to write a little smaller. We have to solve for b. We can use either ordered pair to solve for b. I'm going to use this one. So my c of x, that's the y value. So 6.5 equals your slope 0.51 times x times 10 plus your b value. And solving that equation, you get b equals 1.4. So now our equation c of x equals 0.51x plus 1.4. Our equation for the smuggler, we've got two ordered pairs right over here on the s function. Okay. 10 comma 12.1 and 20 comma 16.5, sorry, 15.5. So your slope is equal to 15.5 minus 12.1 over 20 minus 10, which comes out to 0.34. Okay, so our s of x is equal to mx plus b, so 0.34x plus b. So let's solve for b. I'll use the first equation. The y value is 12.1 equals your slope 0.34 times your x value times 10 plus b. Sorry if you can't see that. And solving that equation, you're going to get b equals 8.7. So your equation for the smuggler's boat equals 0.34x plus 8.7. There's your two equations. Let's move this up. How fast is each boat going? Well, since we have the x value is a time and the y value is a distance, the change in y over change in x is your change in distance over your change in time. So your rate is going to be equal to change in distance over the change in time, which is your delta y over delta x, which comes out to be your slope. Okay. So the cutter is traveling, say is going 0.51, and we're in miles per minute, right? Miles per minute, that's not a very typical unit for rate, or what you would say a boat was going. So let's convert that to miles per hour. So there's 60 minutes in 1 hour. So the minutes cancel and we'll get miles per hour. So the cutter is going 30.6 miles per hour. Okay. And the smuggler is going, the slope of the smuggler was 0.34. 0.34 miles per minute. Let's convert that to miles per hour. So 60 minutes. I want the minutes to cancel. Put minutes on top. 1 hour. So that comes out to 20.4 miles per hour. Okay. So it looks like the cutter has a chance to catch up. It's a matter of time as long as they don't run out of water space. How far was each boat from the radar station at time x equals 0? So when x equals 0, we're finding c of 0. And for the s, we're finding s of 0. So where are they when t equals 0? Or the x value, 0 minutes from when the pursuit began. So we plug that into the c equation. So we'll get 0.51 times 0 plus b plus 1.4, which is 1.4. Okay, and that's miles from radar station. And S of 0 is 0.34 times 0 plus 8.7. I'm just plugging in 0 into our equation up here for the smuggler's position or the smuggler's distance from the radar station. And we get 8.7. Okay, and what part of the linear equation tells you this? Well, the value of y when x equals 0 is called your y-intercept. Okay, let's go to the next page. So enter both of these functions onto your calculator. So we're going to enter the c of x in f1 of x, s of x, and f2 of x. We're going to use, actually, we're not going to do this. I'm going to use the trace function. Trace function to find f1 of x, which is basically, we said that c is going to be there. This is going to be c of 10. Okay, which we know from over here, c of 10 should equal 6.5. So we're able to double check that we did this correctly. Okay, so let's go to our calculators. We're going to add a graph. Okay. And we're going to put in the first one. The first equation was 0.51 x plus 1.4. Enter. Okay. And we'll hit the tab button to enter into f2 of x. We're entering 0.34x plus 87. Enter. Okay. Now, this window might not make a ton of sense for our purposes. They actually tell us how to define this on the next one. Plot both graphs on the view on the same viewing screen. Use 0 to 60 for x and 0 to 40 for y. Use scales of 10 on both axes. Okay, I'm going to show you how to do that. So we're going to go to menu. We're going to go to Windows/Zoom. On our Windows settings, we're just going to go to Windows settings. So X, we said we want to go from 0 to 60. Okay, the X scale, we're going to make that 10. That's what it said in the question. The Y, we're going to go from 0 to 40. And the make the y scale 10. Okay. And enter. That just gives us a little bit of a better viewing window. If you want to see the x-axis and the y-axis a little better, you can start a little bit negative on the x and the y. Okay. Oh, this one I typed in wrong. Let's fix that. Something's wrong with that one. That should have been 0.34x plus 8.7, not 0.87. So hit the tab button and you can arrow up. We'll change that. That should be 8.7. Okay, that looks a little better. If you don't like this, you can move these out of the way. Just hold down that. Hold this down, and that hand should close, and you can move that over there. Okay. So you can see these are going up by tens. That's because we did the scale that way. And then you can copy this down onto your worksheet. Okay. And put this down here. And then use the intersect feature of your Inspire to find the time and place where the cutter catches up with the smuggler. So for the cutter to catch up with the smuggler, we need their distances to be the same. So we're finding this intersection point. Okay, so there's a couple ways to do this. We could do menu. You could either go to geometry like we've done in the past and go points and lines. Oops, hit escape. We don't want that. We go to menu. We go to geometry, number 8. Points and lines, and then go to 4 for intersection points. And then this tells you how to do that. Click on the first graph, click on the second graph. And there's your intersection point, 42.94, 23.33. And the other way would be to go menu, analyze graph, intersection. And then you've got this lower bound, upper bound. Go to the left of your point of intersection, hit enter. Go to the right of the point of intersection, hit enter, and you will see it shows up that way also. I'm going to get out of there so we don't, it doesn't look too messy. Okay. And that's it. That's your intersection point. So let's go back to our worksheet. That means your x value is 42.94, your y value is 23.3. So what does that mean? Well, that means 42.94, that's your x, the number of minutes since the pursuit began. So after almost 43 minutes, after 42.94 minutes, okay, the cutter has caught up with the smuggler, and they are 23.3 miles from the radar station. Let's go back here and we'll finish this. Now I've already done this part here where I've graphed it. So this is what your graph is going to look like. I labeled these going up by tens, labeled these going up by tens. I've labeled time in minutes from the beginning of the pursuit. You want to be as descriptive as possible. This is the y-axis, the distance in miles from the radar station. Okay. Does ask up here, what do you suppose the calculator means by this expression f1 of 10? Well, f1 of 10 is the y value of the function when x is 10. In the context of this problem, we've kind of already defined it, okay? Since we put the c of x equation into f1 of x, this means that the cutter is 6.5 miles from the radar station, 10 minutes after the pursuit began. Okay, and here's our point of intersection. And the very last question on the bottom asks us, we did use the intersection feature, and it says find the intersection algebraically below. So we can do that. To find the intersection algebraically, we're going to set c of x equal to s of x. So you're going to set those equations, 0.51x plus 1.4 equals 0.34x plus 8.7. And subtract the 1.4 from both sides, subtract 0.34x from both sides, and you'll get 0.17x equals 7.3. Divide both sides by 0.17, you get x equals 42.9412, which is exactly what our graph said. And the y value will equal. You can just plug that into either equation. You can plug that in either on this side, or you can plug that in over here. And you should get the same thing because they should be equal. That's the x value that makes these two y values equal. So the y value is 23.3. Okay, so your ordered pair is 42.9412, comma, 23.3. You'll notice the reason that I left that alone, I didn't give you more than one decimal place, is because that's actually an exact answer. Okay. All right. Well, I will post the solutions to all this with the video, but now we're going to do one more problem. Okay. And you go to the next page, which is page 66. This is a review page, but we're going to do this problem 29. Okay. A rematch of the fabled race problem. So coming off an embarrassing loss to the tortoise, the hare wanted a rematch. The tortoise, being a wise old animal, agreed to race again if he was given a 30-minute lead. Both start at the same point. The tortoise races at a constant speed. That's key. It's a constant speed, 50 feet per minute. And the hare races at a constant speed, 160 feet per minute. Okay. And this is nice. They've defined the variables for you. So x is the number of minutes since the tortoise started. Notice the tortoise started. And the hare is giving a 30-minute lead. Okay. And t of x is the number of feet the tortoise has gone, so the distance for the tortoise. H of x is the number of feet, so the distance for the hare. Write these particular equations, and then we're going to find all this. Okay, so I'm going to do this on a separate sheet of paper. I'm going to keep this in mind. I want to organize my information a little bit better. So I know that distance equals rate times time. Okay, so I'm going to set up a table up here. I'm just going to put this up in the corner. I know that distance equals rate times time. And I know I've got a tortoise, and I've got a hare. Okay, they've defined some things for me. X is the number of minutes since the tortoise started. So X is the time for the tortoise. H of X is the number of feet the tortoise has gone. T of X is the number of feet since the tortoise has gone. So that's the distance for the tortoise, the distance for the tortoise. So this right here is T of X. H of X is the number of feet the hare has gone. So it's the distance for the hare. Okay. The tortoise raced at a constant speed of 50 feet per minute. So the tortoise's rate is constant at 50 feet per minute. Okay. The hare races at a constant speed of 160 feet per minute. Okay, now we need the time for the hare. Well, they do tell us this. The tortoise, having been a wise old animal, agreed to race again if he was given a 30-minute lead. Okay, which means if he starts first and the hare starts 30 minutes later, that means the time for the hare is going to be less. It's going to be 30 minutes less. Okay, and this is in minutes. These are in feet per minute. If these were in feet per hour, you might want to use a half an hour here instead of 30 minutes, but these are in feet per minute. So be careful with the units. This is in feet per minute, and this is in minutes. So when you multiply rate times time, this should be in feet. This is feet per minute, and this should be in minutes. So distance equals rate times time. When you multiply these together, you're going to get feet. All right. You don't have to do this. I like to do something like this with distance, rate, and time when it's useful. Now be careful with when we did the other problem, when we did this problem, it was a distance, rate, and time problem. But the problem is they didn't give us that kind of information. Okay? They gave us ordered pairs. They didn't give us the time of one with respect to the other. So it was just a little bit different way to do it, to the problem, because of the information they gave us. Okay, so now if we go through the parts of the problem, this should be a lot easier, right? Your particular equations, t of x in terms of x and h of x in terms of x. Well, t of x equals rate times time. Distance is rate times time. So t of x is simply equal to 50 times x. H of x is equal to 160 times the quantity x minus 30. Or let's simplify that. Okay, you're going to get 16 when you distribute 16 160x minus 4800. That's part A. Part B, find t of 35. T of 35, well, we're just plugging 35 in for x, so 50 times 35, which equals 1750. H of 35 equals, go to the h function, 160 times 35 minus 4800, which equals 800. And now what the heck does that mean? That means 35 minutes into the race. Where are they? Well, 35 minutes into the race, the tortoise is at 1,750 feet. The hare is at 800 feet. So 35 minutes into the race, the tortoise is winning. Okay. Who's ahead? Well, the tortoise is ahead. Okay. And you know that because he's gone, the tortoise, he or she has gone 1,750 feet, and the hare has gone 800 feet. Okay, let's go to C. When will the hare catch up to the tortoise? How far from the starting point? So when will they catch up? Well, they'll catch up when their distances are the same. Okay, so when their distances from the starting point are the same. So when t of x equals h of x. Now you could graph this on your calculator. I'm not going to do that for this one. I'm just going to do it algebraically. So t of x was equal to 50x. H of x was equal to 160x minus 4800. Solving this equation, I'm going to subtract 50x from both sides, so I have 110x. I'm going to add that to the other side, 4800x. Sorry, 4800, there's no x there. Divide both sides by 110, and I would get 43.6864. And that's in minutes. Remember, the x is a time. Okay. And now if we want to know the distances they've traveled at that time, so t of 43.6864 and h of 43.6864 is equal to, and these distances should be the same. We solved for the x value that makes these two distances equal. Okay, so plugging that into your calculator, you will get 2181. 2181 feet. 2181.82. 2181.82 feet. Okay, so that's part C. Let's do part C. When will they catch up and how far from the starting point? So they won't catch up until 2181. Before starting the race, the two animals agreed that the race would be 2,000 feet. Who won? Well, look at that. The hare doesn't catch up until after 2,000. So who won? The wise old tortoise wins again. Okay, and how do you know? You can explain that in words. You could say, because The hare doesn't catch up until 2181 feet, and the race was over at 2,000 feet. Now, who won and by how many feet? That's a little bit harder. By how many feet? Meaning the race is over. The tortoise wins when the tortoise crosses the finish line, when the tortoise has traveled 2,000 feet. Okay, so we need to set T of X equal to 2,000 feet. Find out when did that happen, because we also are going to have to find out where was the hare, okay? Because at the point where the tortoise crosses the finish line, and we want to know how much the tortoise wins by, well, how far behind was the hare at that point? Okay, so the T of X equation is 50x, which is equal to 2,000. I'm going to solve for x, divide by 50. X is equal to, what do we get? 40 minutes. Okay, now we have to look at where was the tortoise at 40 minutes. I'm sorry, where was the hare at 40 minutes? So h of 40 is equal to 160 times x, or times 40, minus 4,800, which equals 1,600 feet. Okay, so when the tortoise is at 2,000 feet and wins, the hare is at 1,600 feet. So the tortoise wins by 400 feet. Okay, I almost forgot one last thing. I said I was going to come back to it. If you go back to the top of this page, number 6, I said we're going to use the trace function to find f1 of 10 or c of 10. And looking at what we did on the first page, c of 10 should be 6.5 on this function. On the other function, s of 10 should be 12.1. Okay, so let's go back to the calculator where we have this equation. We still have, that's not it. We still have this equation in there. And what we want to do is find the value of our function when x equals 10. Okay, this first one, the f1 of x was c of x, f2 of x was s of x. Okay, so I'm going to go to menu, and then I'm going to go to trace, menu 5, and then I'm just going to go to graph trace. Now, the nice thing about this, you can actually move left and right if you hit these arrow buttons, move left and right, and it can kind of move you along the curve. The problem is it kind of locks in on certain points. So if you want a particular function, see right there, it didn't lock in on 10. So what we're going to do is we're in trace mode, so you can move along there, or you can simply, in trace mode, remember, hover over here, it gives you the instructions, cursor left or right to move along a graph, up or down to jump to a different graph. Okay, so if I hit the up button, I can jump to the other graph, and I can see when my x value is 9 down here on the lower right. When my x value is 9, my y value is 11.7. Okay, I can go back and forth by going up and down. I can go right, left along a function. Or it tells me this, and this I think is the most useful. Enter a number to jump to a particular independent value. So an x value, your independent variable. Okay, so now I want 10. So I'm just going to type in the number 10, 1, 0, and hit enter. And it goes to 10. So my input is 10. My output is 6.5. Notice we're on the first one, and that's what it was supposed to be. It was supposed to be when our input was 10, our output was 6.5. Now I can arrow up to the other graph, and I've got 10, and I've got 12.1. Can I move that? I can move my video out of the way. 10 and 12.1, you can move up and down. Now notice, I'm still in trace mode. Okay, so I can put in any value. If I want to put in, what's my output when my input is 20? Just type in the number 20, hit enter. Type in the number 20, hit enter, and it moves to that value. So when x is 20, my y value is 15.5. Arrow down to the other graph, my y value is 11.6. Okay, you can plug in any x value you want, which is really nice, which is really useful. Okay, so we want to go, where do I want to go? I want to go back to here, our paper, so we can see this. Okay, so we said C of 10, it did match, it was 6.5. We also checked the other graph, S of 10 was in fact 12.1. We also checked out the values when X was 20, C of 20 and S of 20. C of 20 was 11.6 and S of 20 was 15.5. Okay. And so on. So that's something that's very useful that I forgot to mention earlier. All right.